Hello, future RMTs. Welcome to this video lecture. And in this lecture, what we are going to discuss is all about assays for enzymatic activity. To start, let us have a recall of what is Michaelis-Menten hypothesis. We all know that the Michaelis-Menten hypothesis of relationship between the velocity and the substrate can be represented mathematically as Vmax S over Km plus S. No? Again, the, the hypothesis of Michaelis and Menten is mathematically represented as V is equals to Vmax, okay, S over Km plus S, where the V is the measured velocity of the reaction, the Vmax is the maximum velocity, S stands for the substrate, Km stands for the Michaelis-Menten constant, and S again is the concentration of our substrate. Remember guys that in 1913, Michaelis-Menten hypothesis hypothesized the role of substrate concentration in the formation of enzyme substrate complex, or what we call the ES complex. According to this hypothesis, the substrate is readily binds the free enzyme at a low substrate concentration. With that, the amount of the enzyme exceeding the amount of substrate. Okay? Therefore, the reaction rate steadily increases as more substrate is added. This reaction is what we call the first order kinetics. Why? It is called first order kinetics because the reaction rate is directly proportional. No? Directly proportional to the substrate concentration. Eventually, however, the substrate concentration is high enough to saturate all available enzymes. Therefore, reaction velocity reaches its maximum. When the product is formed, the resultant free enzyme immediately combines with excess free substrate. And now, that is what we call zero order kinetics, wherein the reaction rate depends only on enzyme concentration. Now, for the measurement of enzyme assays or measurement of the enzyme activity, there are two general methods may be used, no, to measure the extent of enzymatic activity. Number one, we have the fixed time. Wala po tong S. We have the fixed time method and we have the continuous monitoring or kinetic assay. So what is the difference between the two? Once we said fixed time method, the reactants are combined and the reaction proceeds for a designated time. The reaction is stopped. Usually, it is caused by inactivating the enzyme with a weak acid. Then, therefore, a measurement is made of the amount of the reaction that has been occurred. The reaction is assumed to be linear over the time reaction or the reaction time. Therefore, the larger the reaction, no, the more enzyme is present. On continuous monitoring or kinetic assay, multiple measurement. No, tandaan, continuous, multiple. Okay? Multiple measurement. Usually, change of absorbance. Okay? During the reaction. It is either done with a specific interval, usually 30 or 60 seconds interval, or by continuous monitoring of spectrophotometer. Now, for the diagnostic serum enzymology and methods of analysis, the following are the methods. One, For amylase, we have the aminoclastic. We also have the saccharogenic. We also have the chromometric and continuous monitoring. For lipase, we have the Cherry-Crandall, the Tietz modification of Cherry-Crandall, Grindler, Young and Biggs. We also have the Seligson and Damascene. For alkaline phosphatase, we have the Shiniwara, Bodansky, Reinhardt and Jones, King and Armstrong, Bessie, Laurie and Brook. For acid phosphatase, we have the Gutman, Bessie, Laurie and Brook, Babson, Reed and Phillips, Roy et al. And Ritz and Gilbolt. For aspartate aminotransferase, we have the Reitman, Franzel, the Carmen, Babson et al. For aniline aminotransferase, we have the Reitman and Franzel, Orlovsky and Ledoux. For lactate dehydrogenase, we have the Orlovsky, Cabot, dinitrophenylhydrazine, Orlovsky and Ledoux, Berger and Broida. And for creatinine kinase, we have the Hughed, Sachs and Moore, Tanzer and Gilvam, Rosalki and Hera. Let us start the discussion with amylase determination. As we all know, amylase is an enzyme that hydrolyzes complex carbohydrates. Again, amylase hydrolyzes complex carbohydrates. Okay, having said, these complex carbohydrates includes your starch and the liver stored glycogen. Okay, this starch and liver stored glycogen is being converted into maltose and maltodextrin. Converted into maltose and maltodextrin. Okay, it is a glycoside hydrolyzed that acts at alpha 1,4 glycosidic bond. Remember that amylase is produced by our pancreas. Now, for the principles of amylase determination, we have the aminoclastic, we have the saccharogenic, we have the chromogenic, and we have the continuous monitoring. For aminoclastic, it simply measures the disappearance of the substrate. Remember guys that in aminoclastic, amylase is allowed to act on starch substrate to which iodine has been attached, as amylase hydrolyzes the starch molecule into smaller units. Therefore, the iodine is released. On the other hand, we have your saccharogenic, which measures the appearance of the product. The saccharogenic method for the amylase determination uses starch substrates that is hydrolyzes by the action of amylase to its constituent carbohydrate molecule that have a reducing properties. For example, the reducing sugar is then measured where the concentration is proportional to the amylase activity. One of the best examples of saccharogenic method is the Nelson-Somogyi method for our carbohydrates. Last, as a third, we have our chromogenic, which measures the increasing color from the product coupled with chromogenic dye. Remember that chromogenic method use starch substrate to which a chromogenic dye has been attached to produce the chromogen. Okay, and this chromogen is a insoluble dye. Okay, that is an insoluble dye. Take note, as the amylase hydrolyzes the starch substrate, smaller dye substrate fragments are produced. And last but not the least, we have our continuous monitoring, which is a coupling of several enzyme system to monitor the enzyme's activity. Okay, wherein the change in absorbance of the NAD at 340 nanometers, okay, at 340 nanometers is measured at the pH 6.9. Now, what are the practical considerations that you have to remember for determination of our amylase? So we have to separate the serum immediately. If we are going to use plasma, no, we are going to use EDTAs. We have to avoid the use of EDTA, citrate and oxalate. Iodine may cause irritation, and the incubation time should be monitored. By the way, I just would like to go back to the this slide to give an example of amyloclastic and sacharogenic. Like what I've said, so Nelson Somogi is an example of sacharogenic. No? Let us all remember that we have what we call the Somogi sacharogenic method. Okay? Remember that Somogi sacharogenic method is based on the measurement of time that is required for the amylase to hydrolyze starch polysaccharides, and of course, to glucose. Therefore, the rate of the conversion is directly proportional to the amount of amylase in the serum, urine, and even in the spinal fluid. Example of a amyloclastic is the modification of the Caraway. Okay? Modified Caraway amyloclastic method, wherein it measures amylase activity by decreasing starch hydrolysis, no, is evidenced by decreasing starch iodine formation, since amyloclastic is based on the disappearance of the starch substrate. Now, for the sources of error, we have to take note that amylase in serum and urine is stable. However, plasma triglycerides suppresses and inhibit serum activity of our amylase. There are also instances that amylase values are normal in cases of acute pancreatitis with hyperlipidemia. Okay? Another one is the administration of drugs such as morphine and other opiates for pain reliever could also affect the levels of our amylase because it falsely increases, no, the activity of our amylase. Now, for the reference range, you have to take note that 28 to 10 units per liter is the normal unit or normal range of amylase for serum, and 1 to 15 units per hour is for our urine. Leading to next is what we call the lipase determination. No? As we all know, lipase along with our amylase is all enzymes or enzymes that is being produced by our pancreas. No? Remember that our lipase is an enzyme that catalyzes the hydrolysis of the fats. If the amylase is important in the hydrolysis of the complex carbohydrates, our amylase is important in the hydrolysis of our fats. One of those is our triglycerides. If you still remember, in our discussion, we said that lipase is important in the hydrolysis of our triglycerides so that it will give you your glycerol, which is being measured in most of the triglyceride analysis, and of course, the fatty acids. In the action or in the methods for our lipase, no, determination, the triglycerides plus water, no, and the action of our lipase at pH 8.6 to 9 will give you your two monoglyceride and fatty acids. Remember again that no, the deficiency in lipase could lead to high concentration of cholesterol and triglycerides. That is what we call type 5, no, hyperlipidemia, no, wherein there is a deficiency in the lipase. Remember also that serum lipase together with serum amylase are the most common tests for the evaluation of our acute pancreatitis. However, lipase is more sensitive and more specific than our amylase because we have amylase that is being produced by our salivary gland. Now, remember guys that the method for the determination of lipase activity is based on the turbidimetric assay. No? It is based on turbidimetric assay. Okay? The decrease in the turbidity is proportional to the lipase activity of the serum. Again, decrease in turbidity, no? Decrease in turbidity is directly proportional to the lipase activity of the serum. Therefore, quantitative relationship between turbidity to change and the number of lipase or the number of micelles provide is the theoretical basis of the turbidimetric method for lipase. Remember guys that serum lipase hydrolyzes the oil emulsion and it is being done spectrophotomically at 400 nanometers. Okay, we have what we call the Cherry-Crandall method. Cherry-Crandall method is one of the most commonly known method for the determination of lipase activity. No? The classic Cherry-Crandall method uses olive oil and trehaline as a substrate. However, if we are going to compare olive oil and trehaline as a substrate, we can say that trehaline is much more no, uh, acceptable as a substrate for the Cherry-Crandall method. Again, remember that turbidimetric method is a simpler and more rapid than titrimetric, which is your Cherry-Crandall method. Now, what is the difference between turbidimetric method for lipase activity and colorimetric method for lipase activity? Remember, once we said turbidimetric method, it is simpler than the titrimetric assay. No? In this method, cloudy emulsion is being analyzed as the fat is being hydrolyzed by the lipase. On the other hand, it measured as an estimation of the lipase activity. For a colorimetric method for lipase activity, it is based on the coupled reaction with enzymes such as peroxidase and glycerol. Now, what are the sources of error for lipase activity? Lipase is stable at serum with negligible loss in the activity at a room temperature. However, we have to take note that hemolyzed sample is not recommended or not allowed, and it should be avoided because hemoglobin inhibits the activity of lipase that causes false low levels of our lipase. And for the reference range, less than 38 units per liter is the level for our lipase. Next in line is we have the lactate dehydrogenase. Remember guys that lactate dehydrogenase catalyzes the oxidation of lactate to pyruvate with subsequent reduction of NADH to NAD. No? Aside from that, the reaction is reversible and the backward reaction is favored at the reaction equilibrium. Lactate dehydrogenase is commonly found in almost all of the body tissues. That's why we said that lactate dehydrogenase has one of the least specific enzymes because of its specificity, because there are a lot of tissues that can be that can produce lactate dehydrogenase. To name some, we have a heart, liver, kidney, muscle, brain, even the red cells, and lungs. That's why we can also say that lactate dehydrogenase is an example of a hematopoietic enzyme because it has an activity in our red cells. Now, like what I've said, there are two methods that is it being involved for lactate dehydrogenase termination. We have the forward method and we have the reverse method. So what is the difference between the two? Once we said forward method, it is known to be your rocker method. And once we said reverse, it is known to be your Prolobsky method. So what is with Walker method? In Walker method, no, Walker method is a forward method for the quantification of our lactate dehydrogenase activity that utilizes the oxidation of lactate to pyruvate. Okay, that oxidizes or that utilizes the oxidation of lactate to pyruvate with the formation of no with the formation of our NADH and NAD. Forward method or Walker method is read spectrophotomically at 340 nanometers, okay, which allows kinetic assay to be performed. On the other hand, we have your Orlovsky-Ledoux, which employs the reverse reaction from pyruvate, from what happened? From pyruvate to lactate. Okay, therefore, in this situation, the NADH serves as a co-substrate and is being consumed during the course of the reaction. Take note, Orlovsky-Ledoux is also an example of a kinetic assay, okay, and being read also at 340 nanometers. Okay, so that is the difference between lactate dehydrogenase reverse and forward method. Now, one of the most common sources of error in the lactate dehydrogenase analysis is hemolysis, since we all know that lactate dehydrogenase has an activity in our red cells. Next in line is we have the creatinine kinase determination. For creatinine kinase determination, it allows the creatinine kinase determination. It is also known as our creatine phosphokinase, or in some references, they call it as CPK. In some references, they call it as the CPK. Creatinine kinase could be considered as a more specific as compared to our lactate dehydrogenase. Why? Because it is found mainly in three major organs: heart, brain, and even skeletal system or muscles. Thus, increased levels of CK can be observed in cases of heart attack, skeletal muscle injury, and strenuous exercises or activities, or even alcohol consumption. Remember, guys, that creatine kinase catalyzes reversible phosphorylation by creatine by ATP. Creatine by ATP. The ATP and the glucose are converted. Okay, the ATP and glucose is being converted, okay, to ADP and glucose 6-phosphate by hexokinase. So we have creatine phosphate. This is what I'm telling, plus ADP, and the action of CK, it will give you your creatine plus ATP. Your ATP will react ATP plus our D-glucose, no, through the action of the enzyme hexokinase will give us our glucose 6 phosphate, and your ATP will be converted into ADP. Now, our glucose 6 phosphate, no, plus our NAD will react in the presence of our glucose 6 phosphate dehydrogenase, no, to produce your glucose 6 phosphate dehydrogenase. Dehydrogenase, okay? Will react, no, to form your 6 phosphogluconate plus NADH plus your hydrogen. Okay? So, like our lactate dehydrogenase, we have what we call the forward and the reverse reaction. So, what is the forward reaction? For the forward reaction, we have the Tanzer-Gilvard, no, method, which assess the rate of forward reaction in which creatine, no, creatine is converted to, no, to creatine phosphate. Okay, while Oliver Rusalki, a reverse method, is produced, no. Oliver Rusalki is a reverse method wherein creatine phosphate will give us our creatine, no? So reverse lang. Instead of creatine to creatine phosphate, we have creatine phosphate to creatine. So that is the difference between the reverse method and the forward method for creatinine kinase determination. Now, what factors inhibits the activity of our creatinine kinase? Number one, excessive ions such as chloride and sulfate. Chloride and sulfate, no, inhibits the activity of our creatine kinase. Heavy metals such as zinc, copper, no, and manganese ions, no, can inhibit also the activity of creatinine kinase. Iodoacetate and other sulfhydryl binding agents, no, excessive ADP, citrate, fluoride, and L-tyrosine, and even excess uric acid inhibits the activity of our creatine kinase. Okay? So what are the sources of error ng ating hemolysis o ng ating creatine kinase? Number one, we have hemolysis. Number two, physical activity, since strenuous exercises could affect the level of our creatine kinase. Now, what are the reference range? So for male, 46 to 171, for female, 34 to 145, and for the CKMB, one of the isoenzymes of the CK, less than 5%. Remember, guys, no, take note that our creatinine kinase could be an enzyme that assesses the cardiac function, no. Particularly, one of the diseases is the acute myocardial infarction. In acute myocardial infarction, along with, no, CK and ALD, LDH as well as AST. Okay, we have here the table, no, that shows the elevation, the peak, and the duration levels of our CK. And if you can see, our CK creatinine kinase, no, will elevate first 4 to 8 hours, no, with a peak of 12 to 24 hours, and the peak of elevation and the elevation could be seen into 3 to 4 days. our CKMB, which is an isoenzyme specifically for our heart activity, no, 48 hours. Peak activity is between 24 to 38 hours, and the duration level is up to no uh 2 to 3 days, no, 2 to 3 days peak level. For AST, our first, first non-specific enzyme that will increase, take note, the first non-specific enzyme that will increase in cases of acute myocardial infarction is AST. Elevation is 8 to 16 hours, no? The elevation is 8 to 12 hours rather. No, peak level is 24 hours, and duration is 5 days. And last but not the least is our lactate dehydrogenase, which is increased, no, for elevation 12 to 24 hours. Peak level is 72 hours, and the duration is for 10 days. Okay. Next in line is we have the alanine aminotransferase and the aspartate aminotransferase. This is your ALT and your AST. No? ALT and your AST. Now remember guys that aminotransferase, both of this is classified as aminotransferase. Remember that both of these enzymes, aminotransferase, catalyzes the transfer of the amino group from alpha amino acid to keto acid, forming what we call new amino acid. Okay? Forming what we call new amino acid. All right. For that, no, aniline transferase is formerly known as our serum. Serum what I'm saying is ALT aniline is serum pyruvic transaminase, no, the SGPT, and for the aspartate is we have your serum oxaloacetic transaminase or the SGOT. Okay, both of these enzymes has an activity in the liver, heart, muscle, pancreas, and kidneys. Remember that both of these enzymes could be measured in what we call Harman method. No, wherein in Harman method, no, the enzyme glutamic transaminase catalyzes the conversion of aspartic acid, your aspartate, and alpha ketoglutarate to what we call glutamic acid, your glutamate, and oxaloacetic, your oxaloacetate. The keto acid oxaloacetate or oxaloacetic acid, no, reacts with our dinitrophenylhydrazine. What's happening with my pen? Dinitrophenylhydrazine. Okay, that reacts with our dinitrophenylhydrazine to form a keto acid hydrazone upon the addition of sodium hydroxide that yields an intense brownish color, which can be read spectrophotometrically, no? Which can be read photometrically, no, at a desired wavelength. Okay. Now, for the Rateman-Franzel method naman, no, the endpoint reaction, that is an endpoint reaction, okay, wherein it catalyzes L-aniline and a ketoglutarate to form your pyruvate and glutamate. The pyruvate will react with 2,4-dinitrohydrazine, no, 2,4-dinitrohydrazine to form your pyruvate, no, and you have your 2,4-dinitrophenylhydrazone, which is measured at 505 nanometers, no? Which is measured at 505 nanometers. Again, both aniline aminotransferase and our aspartate aminotransferase is measured using Carmen and even in Rateman-Franzel method. Okay, sources of error is for AST hemolysis. For ALT, we have relatively unaffected by hemolysis. And for the reference range for AST and ALT are as follows. Okay, next is we have our acid phosphatase determination. So what is with acid phosphatase determination? Acid phosphatase is an enzyme, no, that hydrolyzes the phosphate ester bonds at acidic pH. Ayun, tandaan natin. That hydrolyzes, no, ester bonds at acidic pH. It is found in high concentration in the cellular components of the bone, spleen, and even in the liver, as well as in the intestines and the blood. Although our acid phosphatase is significant levels of our acid phosphatase, no, appears in several tissue, prostatic phosphatase have the greater clinical significance, no, of interest, since elevation of isoenzyme occurs in the serum of a patient with prostatic carcinoma with the presence of metastasis. Now, for acid phosphatase determination, we have these two well-known method, the Roy et al. Method and the Babson, Reed, and Phillips method. Okay, number one, the Roy et al. Method. In this method, no, the determination of acid phosphatase involves the hydrolysis with the use of sodium thymol naphthalene, wherein the addition of the alkaline terminates an enzymatic reaction and simultaneously develop a blue color. Okay, develop a blue color. Take note that the intensity of the color is measured at 590 nanometers. And the intensity of the blue color is proportional to the enzyme activity. On the other hand, we have the Babson, Reed, and Phillips method. This method, no, the acid phosphatase activity can be measured by the release of alpha naphthol. No, by the release of alpha naphthyl phosphate, no, that reacts with water, which is then coupled with the fast red TR to give our diazodide, which gives us your chromophore. Take note, guys, that the alpha naphthol released from the substrate alpha naphthyl phosphate by acid phosphatase is coupled with the fast red PR to produce a colored complex which absorbs at the light at 405 nanometers, no? Which absorbs light at 405 nanometers. Take note that the reaction can be quantified photometrically because of the coupling reaction is instantaneous. Now, since, like what I've said a while ago, no, one of the most common application of acid phosphatase is for our prostatic involvement. Correct. Remember that we have your L-tartate. L-tartate, take note that L-tartate inhibits prostatic acid phosphatase. Okay, prostatic acid phosphatase, but does not interfere with the reaction mechanism. Therefore, if we want to measure, no, our prostatic acid phosphatase, no, the presence, okay, if the testing is performed in the presence of our L-tartate, the difference between the results of the assay, no, the absence and the presence of L-tartate, no, is an indicative of our prostate acid phosphatase activity. Again, yung L-tartate po natin ini-inhibit ang activity ng ating prostatic acid phosphatase. Therefore, if we're going to measure the activity of our acid phosphatase in the presence and in the absence of our L-tartate, the difference between those two indicates, no, the activity of our acid phosphatase. Okay, indicates the activity of our acid phosphatase. So what are the different methods for acid phosphatase determination? We have the Bodansky, the Gutman, King, Armstrong, the Hudson, the Babson, Reed, and Phillips, Roy et al., and we also have the Rates and Gubalt. No, these are the substrates used. No, the substrate used by our activity. No, and the comments. No, and the comments. Now, what are the sources of error? Remember, guys, one of the sources of error for our acid phosphatase is fluoride. Why? Because fluoride inhibits the activity of our acid phosphatase. Therefore, proper selection of anticoagulant is important. Aside from that, oxalate and heparin have been shown to produce decreased activity of our acid phosphatase. Okay, storage condition is also critical. Okay, storage condition is also critical since pH and prolonged storage at room temperature both resulted in the loss of the activity of the enzyme. Now, if there is one factor that causes significant error or major factor that causes significant error in the level of our acid phosphatase, there is no other than hemolysis. No? The major factor producing false elevation of our acid phosphatase is hemolysis. Bakit naman? It is because our erythrocyte contains significant amount of our acid phosphatase. Therefore, loss of enzyme from the cells strongly influences the concentration of our acid phosphatase obtained in our serum or even in the plasma. That's why failure to use an anticoagulant result in the release of our enzyme from platelets that contributes to the increase in the amount of our enzyme that is being measured. Take note, guys. Take note of this. In methodologies that measures the product of the formation of our acid phosphatase at 410 nanometers or near the wavelength, hemoglobin and even your bilirubin in high concentrations produces false elevation in the activity of our enzyme. Again, kapag po ang ating wavelength is set at 410, high concentrations of our hemoglobin and even our bilirubin can contribute to the problem or false elevated enzyme values. So please take note of that. And I guess this is the last. We have your alkaline phosphatase determination. Ano lang yung pinagkaiba ni alkaline phosphatase at ni acid phosphatase? Yung acid phosphatase, nagre-require siya ng acid pH while our alkaline phosphatase requires alkaline pH, at pH 10.5. Or usually, 7.5 to 9.5. 10.5 is for bacillary and Brook. Now, what is with alkaline phosphatase? It hydrolyzes enzyme that catalyzes the cleavage of esters of phosphoric acid again at alkaline pH. Remember that our alkaline phosphatase is responsible for the removal of the phosphate groups, and that is what we call the phosphorylation. I will write. Okay. Again, it could be done in the between pH 7.5 to 9.5. 7.5 to 9.5. Remember, guys, that our alkaline phosphatase has an activity in the liver because it is being synthesized by the hepatocytes of the liver. It is present in the various organs such as our bones, intestines, and in the placenta. Kaya nga tayo yung tinatawag na placental, placental LDH, placental alkaphos or ALP, the regan, the intestine, the bone, and the liver. Take note that the placental alkaline phosphatase is heat stable while the bone, sulat po natin yan, the placenta ALP is heat stable while our bone ALP is our heat labile. All right. Okay. So we have what we called the Bessie-Lowry and the Brook method. In this method, the para-nitrophenol phosphate or the para-nitrophenol, when buffered at pH 10.5, is hydrolyzed by alkaline phosphatase into para-nitrophenol and phosphate. What will happen is that a yellow-colored chromogen of para-nitrophenol is produced when the solution is treated with diluted sodium hydroxide. With diluted sodium hydroxide, whose absorbance is proportional to the activity of our alkaline phosphatase. Remember, take note, tandaan po natin, that alkaline phosphatase acts upon the AMP buffered sodium thymolaphthalin, monophosphate, and the addition of our alkaline reagent will stop enzyme activity and simultaneously develop again a blue chromogen, which is then measured using photometric assays. So these are the methods for our alkaline phosphatase determination and the substrate used, as well as the comments for our method. And that concludes our discussion. And allow me to greet you happy holiday season. Enjoy the rest of the Christmas vacation and good luck on your final examination.